Let's see hands-on workshop on how to perform mesh convergence. So we will take the previous model, that is plate with hole example, and since we understood that second order elements are more accurate in terms of capturing stress gradients, so we will continue with no second order TET elements, that is C3D10, for our mesh convergence study. So this is our previous model uh, where we have meshed this hole with 1 mm element size, and global element size is 2.5 mm. Okay, so for 1 mm element size, the stresses are, the peak stress is 313 megapascal, and from previous chapter we know the peak stress analytical from analytical calculation is 323 megapascal. Okay, so now for this model, let's see what is the stress gradient. Okay, so we need to go within these steps. Okay, and we have this field outputs EF. NF is a nodal output, EF is elemental output. So I will double click this, and the default output variables are S and E. S stands for stresses, E for strains. Okay, so these are standard uh, output variables for Calculix. So you can drop down this and see there is something called ERR. Okay, so ERR, as we said, it is a gradient error estimator. It reports the stress gradient within element and or stress gradient between adjacent elements, okay, from one to another element. So I will select this output ERR. Okay, now we can see SEERR and say OK. I will run it again. So I will see ERR output here. Okay. So if we see in a peak stress, this is the peak stress, and our stress gradient here is somewhere around 14 percentage, okay, in green. So if I can probe also from here, tools, query, and you can probe here. So it is almost 10 percentage. Okay. So depending on your standard, okay, how much error you are accepting, we need to go further. For me, the 9 percentage of stress gradient is not sufficient for this example. Okay, so I will do further mesh refinement. Okay, now we can see the maximum gradient is in this location, okay, which is 22 percentage, but we are concentrating here because the maximum stress is here. Okay, and we will see like why the maximum gradient is in this location in a while. Okay, but first let's focus on the mesh convergence in a max stress location. We can remove these annotations. Okay, so I will further refine this with 0.5. Okay, the mesh is refined, but on this edge element is very big, so let me refine in this edge as well. I will create another mesh refinement. Let's use 0.5 mm as well in this edge. Now it looks okay because this is my max stress location. I have refined along this edge as well. So let's create analysis. See TET C3D10 zero point 0.5 mm. Let's run this and see the results. Okay, now the maximum stress is, as we can see, it is 323 megapascal, which is almost close, or it is equal to our analytical calculation. Okay, 323. And let's see the error here. Okay, uh, in this, as I said, is the maximum gradient. We will see this later, but here if we see the maximum uh, stress gradient error is almost negligible. Okay, it is less than 3. So I can go and crop this. It is a 3.5 percentage. In this it is 3.5. Okay. So, and we can see we have dropped stress gradient or gradient estimator from 10 percentage to 3.5 percentage, and stress we have improved from 313 megapascal to 323 megapascal, which is equal to our analytical stress calculation. So this is how using ERR we can perform mesh convergence study. However, no, this helps in uh, from for this simple example, it is very clear. If I go to the previous 1 mm size, okay, and plot one mesh stress, I can see the stress here is 313 and this value is 280. Okay, so 50 megapascal. Okay, the difference from here to here is 50 megapascal, and I have only two elements to capture 50 megapascal difference. So sometimes even by visualization of contours we can easily say that this mesh is not adequate, okay, to capture the stress gradient. So there are two ways. Either from experience you can just look at the contours and decide uh, the need of mesh refinement, or check the output, that is ERR. So now let's discuss about mesh convergence guidelines. Okay. So using ERR for mesh convergence in FEA, as we understood, this is a quick recap. High ERR means high stress gradients and fewer elements. So it is a clear indication that mesh is inadequate and we need a further refinement. So this there is a if you are given a FEA model, and this is a simple approach, okay, to perform a mesh convergence study, okay, using ERR or using no visualization of stress contours. So start with a moderate coarse mesh and run an initial analysis, because when we are given model, okay, geometry, and we are running FE analysis, we are unaware of where is the maximum stress location, how much is the mesh size needed. So we should not start with very fine or refined mesh in a complete model. What we should do for a first cut analysis, we should start with a moderate coarse mesh. Okay, once the first cut analysis is completed, identify local stress gradients, okay, or maximum stress locations. Then check ERR, okay, to know whether in this max stress location there is a need of mesh refinement or not. Okay. As I said, sometimes visual observation of stress contours are also helpful to know the need of refinement. Okay, so this is how we do. This is a simple approach. Now, do refinement only where required, that is critical areas. Okay, as we have seen in this simple example, we perform refinement only near the hole. Okay, this is simple examples. Even for big assembly level model, this rule applies. Okay, you have to track the maximum stress locations and critical areas, and you need to do a refinement only in those areas. Why? Because uh, this reduces a computational time. Okay, we are avoiding unnecessary refinement in non-critical zones. This is one reason. Another reason is fine mesh also converges slower than relatively coarse mesh. Okay, so this is one reason. Since we have not gone into non-linear, this is uh, this is not I cannot explain it now, but just take it as my word that the fine meshes are very difficult to converge. Okay, more than refined mesh if you go, okay, then it is sometimes never able to converge. So always no do a sufficient refined mesh. Okay, don't go too much refined mesh, because too much refinement means the model may not converge. Okay, the fourth guideline is refine until ERR reduces below acceptable value. We have seen this, and this is another additional tip. Okay, in critical regions, use a uniform element size as much as practical. Okay, if we have like 1 size, try to maintain 1 to 1.2 element size in critical zone, okay, critical area. We should not go like 1 to 2 Okay. Other thing is that ensure smooth transition from fine to coarse mesh away from the critical region. Here, no, for example, in this particular example, okay, here as we said, we should use a uniform mesh size. Okay, here, and when we go away from the critical region, okay, we should not use sudden transition of mesh. Okay, if this is 0.5 mm, this should not be a 1 mm or 1.5 mm. If this is zero point 0.5, this should be like zero point 0.7, something like that. Then this should be a 1 mm. So there should be a smooth transition of mesh size, okay, going from critical to non-critical zone. And this is nowadays in most of our softwares very feasible. Okay, they auto when we give a mesh controls in no, look for a local refinement, the software automatically does a smooth transition, okay, from fine to coarse mesh. Okay, so this is simple guidelines, okay, and very easy to follow. Let's write down some key takeaways on mesh convergence. So we have said here, okay, do a refinement only where required, and do a refinement only up to certain, okay, up to certain amount of mesh size. Okay, do not refine too much. So first thing is accuracy. That means we need to maintain balance between refine too much refine or too coarse mesh. Okay, so how it affects the accuracy, let's see, and other parameters, the computational runtime or computational time, and convergence behavior. So this example we have showed for first order tet, sorry, second order tet elements, but mesh guidelines applies universally, okay, for any element type, hex element as well. So if we do a too much refined mesh, too refined mesh means more than requirement, okay, and this is the most engineers do a mistake. Okay, they hit with the convergence issues, and first thing they think that refine the mesh. That is not correct. Okay, if you refine the mesh, your convergence behavior will become even more worse. Okay, so never do a refinement if you are facing convergence issues. Okay, I mean after a point of mesh convergence, you don't need to refine. So too much refinement, accuracy is definitely high. Okay, but we don't need that much accuracy. We already would have achieved the accuracy with mesh convergence. Computational runtime, it is very high, and as I said, the convergence behavior is very poor. Okay, so there is a logic behind this. There is an explanation based on Newton-Raphson method. Okay, but for now, take it that no, too much refinement, relatively convergence behavior is poor. Then refined mesh. Okay, mesh refined. What is the refined mesh means? Just okay, okay, based on our mesh convergence. So that is our refined mesh. What is the accuracy? Very good, because we have already performed a mesh convergence here. The computational time is okay, or we can say justified, okay, because we need some accuracy of the results. Okay, so this computational time is justified, and convergence behavior is good. Then comes coarse mesh. With the coarse mesh, that means in our example we have done with 1 mm size or 2 mm size. Okay, we are compromising with the accuracy of results. Of course, computational time will reduce, or low computational time, and convergence is fast. But this is the main point. We cannot compromise with the accuracy. Then comes a very coarse mesh. This is like for our example 1 mm. Okay, this very coarse is like 2 mm, 3 mm. Okay, so here again we are compromising with the results accuracy, and we cannot say what is the computational time. Okay, because two coarse mesh means the convergence is not guaranteed. Okay. Maybe for this example it might converge, but when we work on actual projects with the multiple components interacting and contacting, the very coarse mesh doesn't guarantee convergence. So not guaranteed, because very coarse mesh means the model is very stiffer, and the behavior in FEA is far away from the actual behavior of the problem. Okay. So we may not guarantee the convergence, and that's why we cannot say what is the computational time. And of course, we should not use very coarse mesh. This is not recommended. Okay. This is also not recommended. So we should always use refined mesh. That means what is the refined mesh size? Okay, so size is we cannot say what is the size. It depends on the problem. Okay, so basically this is from mesh convergence. Okay, so the key takeaway is that we need to strike a balance between accuracy, computational time, and convergence behavior when selecting a mesh size. So that's on mesh convergence. We need to discuss few more things. Okay, we want to go little deep into post processing of results, not on mesh convergence, but some other aspects. So let's take this example. Now, when selecting a max stress location, okay, we also need to consider the nature of the stress. Okay, whether it's a tensile or compressive. Okay, so the from this, okay, we can easily say that this is a max stress location. but we cannot say that this max stress location is a critical location, because the one mass stress is from the value of one mass stress we cannot say whether this is tensile or compressive, and we know the failure location is always tensile. Okay, the tensile stresses causes the cracks to open, so and not a compressive stresses. So first we need to see whether this location is compressive or tensile. So that's where the principal stress outputs help us. So let's see the principal stress outputs. So we have this principal max, principal mid, and principal mean. So sigma 1, sigma 2, and sigma 3. As we know, the principal stresses are always in decreasing order. So sigma 1 greater than sigma 2 greater than sigma 3. So let's see how to say whether this is a tensile or compressive. So we'll plot maximum principal stress, and we will see here the sigma 1 is 314. Okay, at the same location we will also see sigma 3, okay, which is also plus 3. Okay, so sigma 1 is 314 and sigma 3 is plus 3. So both are tensile. Plus means tensile, and minus means negative or compressive stresses. Okay. So at this location, if we observe, the sigma 1 and sigma 3 both are tensile or positive. That means the overall picture of this location is tensile nature. Okay. So from these principal stresses, it is we need to identify the tensile or compressive. There is also very important output available in Calculix or PrePoMax. Okay, without looking at this sigma 1 and sigma 3, you can simply check this sign max absolute principle. Okay, and this will tell whether this is a compressive or tensile. So basically, it is a absolute principle. So absolute principle means uh, the for example, we have, okay, sign max absolute principle. Okay, so let's try to understand this the significance of this output. Let's say sigma 1 is 230 megapascal, sigma 2 is 200, okay, and sigma 3 is 100. Okay, in this example all are positive, so we can say absolute principle. So we take the mode of this, okay, and max absolute, so obviously this is the max. Okay, and sine of this, so the output is 230. Now let's take another scenario. Sigma 1 is 230, sigma 2 is minus 10, and sigma 3 is minus 250. Okay, so here absolute principle, okay, maximum absolute principle, so we'll take first absolute of this. Okay, and maximum absolute principle is this one. Okay, and sign of that is again minus. So here in this case the output of this is minus 250. In short, whichever is maximum in a with a sign. Okay, so that is the output of sign, and here we can see this output clearly tells, okay, whether that particular location is positive or negative. That means tensile or compressive. So let's go back to our PrePoMax. So here we can see all the values, okay, above this red green region they are tensile, and all the values which are of this blue region, okay, they are compressive. So here we can see this region is mostly tensile and this is a compressive. Okay, so there are two ways: either you check this output sign max absolute principle, or check principal sigma 1 and sigma 3. Okay, so this is quite fast. Okay, so this is the significance of principal stresses. Okay, not one message stress only, but we need to check the nature of stress. Okay, whether tensile or compressive. Okay, the next I wanted to discuss on ERR. Okay, as we understood that ERR in this location was 10 percentage, okay, with 1 mm size, but here we see highest stress gradient. Okay, if I this is with 1 mm element size. Further, we did a refinement and we used the 0.5 mm element size, and the error further increased in this location. Okay, uh, the 1 mm size showed 20% stress gradient, 0.5 mm is showing 30% stress gradient. Okay, it is increasing. The reason is that this location, as we know, is a transition from tensile to compressive. We have seen this. Okay, you can see this is a this is a tensile and this is a compressive, and in between somewhere here there is a transition. Okay, there is a sudden transition from compressive to tensile. Okay, and that is the reason we will always see the high stress gradients in this location. Okay, irrespective of mesh refinement, if you further refine it 0.25 mm or 0.1 mm, 0.05 mm, this stress gradient error is not going to reduce. Okay, because this is the nature of problem. Okay, this is the actual behavior. There is a transition from tensile to compressive, and we know this for this simple example. It's just no, by looking at deformation pattern, we know like this is a tensile and this is compressive. Okay, so what is the takeaway from this is that okay, we should know the stress gradient error. Okay, err high doesn't mean it is error high. Okay, it may be a transition from tensile to compressive.